Thank you so much, everyone that's joining us. We are thrilled to kickstart the EC'24 tutorials with two experts on strategic communication, Elliot Lipnowski from Columbia and Doron Ravid from Chicago. And they will be talking about credibility, strategic communication, and information design. So I'll let you, thank you so much for organizing this, and I'll let you take the mic.
Thank you very much for having us and for organizing what looks like it's going to be a really amazing conference. So let me kind of jump right in. The starting point for this tutorial is kind of a big one, which is the observation from information economics, which is information matters for economic outcomes. And once you kind of realize that, you want to start asking, okay, what is the value of people's information? What do people know? And to answer that question, you'd usually want to start with, well, where do people get their information from? Now, there are, of course, a lot of different sources that people get information from. They can do research, or they can learn by observing others. And in this tutorial, we're going to focus on communication. So this is information that's transmitted from one person to the other. An important feature of this communication, as I've already sort of said, is that it has to involve multiple agents. At the very least, you need to have two. You need to have a sender, often called the sender S, and refer to the sender as a she. This is a person who possesses information and sends messages to others. And you need to also have a receiver, often call that R or a he. And that's a person who lacks information and is going to receive these messages from the sender. Now, in an ideal world, the sender would communicate what she knows to the receiver. But in reality, communication is often partial. And so the thing you'd like to understand is what prevents the simple information transmission, and therefore what will be the information that's going to be communicated at the end of the day. Now, if you look at the classic kind of literature that studies this question, like in, let's say, in game theory in the 70s and 80s and 90s, and even the early 2000s, that literature focused on the fact that the sender often wants to lie to the receiver as being kind of the main impediment to communication. So particularly the sender, would like to misrepresent what they know in order to get the receiver to take actions that the receiver thinks are, or so that the sender finds favorable. And so then that literature focused on kind of figuring out what prevents the sender from lying, what makes the sender's communication credible. And the whole different myriads of things that can generate this credibility, and Elliot will talk about some of them in his part of the tutorial. There can be interaction over time, costly signaling, verifiable disclosure, information can be mediated by some disinterested party. But one kind of question that this literature sort of didn't really think of asking is, what would happen if the sender's credibility was guaranteed? So the sender could just communicate whatever information they wanted to the receiver. And the only impediment that faces the sender is the fact that the receiver is a rational Bayesian. And that is the topic of the famous Bayesian persuasion paper of Kamencha and Genskow, sort of asked, if you have the only constraint of communication being, the receiver being Bayesian, what information would the sender want to communicate? And the key observation of that paper is that often the sender would like to hide information from the receiver, even when the credibility of the communication is guaranteed. And this is generating a strategic impediment to communication that has nothing to do with credibility, with the ability to sort of communicate information in an honest way. Now, by posting sort of the question of what information senders want to communicate, this Bayesian persuasion started this extensive literature on information design. But the paper also gives us a benchmark for evaluating the role of credibility in communication. By giving us a model or program that allows us to ask what information would the sender communicate if credibility was not an issue, we can then compare the outcomes in that model, in the Bayesian persuasion model, to the outcomes you would get in models with credibility constraints to see how the need to generate credibility for communication impacts the information transmission between the sender and the receiver. And notice that once you've seen the Bayesian persuasion paper, you realize that credibility is no longer guaranteed to reduce the informativeness of communication, because now it is possible that the fact the sender has constraints on what they can communicate is going to force the sender to change the information they send, potentially in a way that makes it more informative, but maybe even in a way that makes it just sort of incomparable. So, the thing I'm going to try to focus on in this tutorial is the literature that asks, how does credibility impact information transmission using Bayesian persuasion as a benchmark? Now, one impediment for that sort of analysis, at least at the beginning, is that the Bayesian persuasion model and the classic model use sort of different languages of analysis. Bayesian persuasion uses something that's known as a belief-based approach, which we'll talk about in this tutorial, whereas most of the classic communication models will use an approach I'll call outcome-based or action-based, where they're sort of trying to understand what actions are going to be taken in different states or what messages are going to be sent. And this is not completely true. There are some classic strategic communication models that relied on beliefs. Mostly, if you look at the classic Aumann-Maschler and Aumann-Maschler-Stearns sort of repeat games of incomplete information papers and sort of literature on long cheap talk, but most of these papers do not. And so at this stage, that means you have sort of two ways that you could go in order to kind of ask this question of how does credibility impact communication. You can either try to take Bayesian persuasion and apply sort of a more classical approach to it. There are certainly some papers that do it, mostly not for studying credibility, but mostly for studying information design. That is often what is known in the literature as the Bayes coordinate equilibrium sort of approach. Or you could try to take the belief-based approach and try to apply it to models with partial credibility. And it's those kind of models that are going to be the focus of this tutorial. So in today's tutorial, we're going to have kind of two parts. The part that I'm talking about now is going to kind of go over the two extreme points of credibility. So we'll talk about the guaranteed credibility model. So this is this Bayesian persuasion model, which a lot of people probably know, but we'll review that. And then the other extreme case is the case of no credibility, which would be the case of cheap talk. And then in the second part of today, which Elliot will do, we'll talk about models with partial credibility. So models where the credibility is sort of somewhere in between, kind of having absolutely no credibility and absolutely no ability to commit to any messages, and the case where you can just communicate anything that you want. So the plan for this first part, as I kind of already highlighted, I'm going to start by looking at the full commitment case. So we're viewing the Bayesian persuasion model and the belief-based approach in that setting. And then I'll talk about the case with no commitment, which is going to be a model of cheap talk. Now, it turns out that to apply the belief-based approach to models of cheap talk is kind of hard. It doesn't actually give you that much tractability. But one case that it does turn out to deliver a lot of tractability is the case where the sender's preferences are state independent. And that's kind of the topic of my paper with Elliot. And so I'll go over the application of the belief-based approach to that special case. And we'll sort of talk about the two, let's say, main belief-based tools for analyzing those kind of problems, which one we call securability and the other is quasi-concatenation. And hopefully I'll have enough time to also show you exactly how we can apply that to a particular application, which I'll call the think tank. So this is where I'd like to go. Let me sort of now jump into the first half of this part of the tutorial. So the model we're going to look at is what is known as the Bayesian persuasion model. So we're going to have a sender and a receiver, and the sender will be communicating to the receiver about some stochastic state of the world theta. Is going to have some prior distribution mu naught that both players know and share. The receiver will be taking some action from some set A. The sender ends up sending messages from some set M. And both the receiver and the sender care about the receiver's action and the state. The sort of timing of events that you want to have in your mind when you're thinking about the Bayesian persuasion model is one that starts with the sender committing to what is known as a Blackwell experiment. So this is a mapping that takes states and tells you for every state what is the conditional distribution over messages that the receiver will see given that state. You can think of this experiment as being some physical research or maybe an actual physical experiment whose outcome is kind of publicly released and viewed by everybody and can be verified. Then after the sender commits to this Blackwell experiment, which the sender is assumed to be able to commit to any such experiment, nature is then going to draw the state, and given that state, draw a message from the experiment. And then the receiver will see the message and take an action, knowing, of course, what the experiment that the sender committed to at the beginning. Now, when looking at these models, you could do almost everything with like infinite spaces to at least, standard Borel spaces, for at least compact metrizable. But for the tutorial, I will focus on spaces that are finite. And generally, I'll kind of assume that the message space is as large as I would want it, just to make sure that sort of the cardinality of messages is not preventing us from, or preventing the sender from communicating whatever information she wants. So this is kind of the timing of events. What is the solution concept that we're thinking about when we're sort of analyzing a Bayesian persuasion model? Well, that is what is known as perfect Bayesian equilibrium. And it consists of sort of a triplet of maps. The first is the sender's Blackwell experiment. So this is the experiment that the sender commits to at the beginning of the game. Then there is the belief map that tells us for every message that the receiver sees, what is their posterior, or what is his posterior belief over this payoff state given that message. And finally, there's the receiver's strategy that tells us for every message that the receiver sees, what potentially mixed action the receiver is going to take given that message. Now, of course, not every triplet like this is a PBE. For a triplet like this to be a PBE, it has to satisfy the conditions that the receiver is a rational Bayesian. So this rational Bayesian requirement, reduces to two things. The first is that the receiver is Bayesian. So this means that the Bayes rules holds. So the probability that the receiver assigns the state theta given message M times the probability the message M happens has to be equal to the probability the message happens given the state and the probability that state happens. And second, the receiver needs to be optimized. Okay, so that's the rational part of the rational Bayesian. And this is just telling us that for every message that the receiver sees, the receiver must take an action that maximizes his expected utility given the belief that they have after seeing that message. Now, one thing that doesn't show up in this definition is the sender's incentives, right? They do not enter this equilibrium definition. And that is kind of by construction. We're interested in understanding what the sender can communicate when their incentives are not a problem. This, of course, makes you wonder, why do we even have the sender there? Well, we have the sender there because we're interested in understanding, what is information would the sender want to communicate in an ideal world, which we formalize by asking the question of, or trying to find, what is the sender's favorite perfect Bayesian equilibrium? So in particular, the Bayesian persuasion program wants to maximize across all sort of C pi alpha maps the sender's expected utility subject to this triplet of maps being a perfect Bayesian equilibrium. Okay. Now, this program that's worth highlighting, it takes kind of a design-based approach in that we're not thinking about how the sender's choice is made. We're just thinking of the sender as being able to both commit to this information structure, but also because they're sort of very somehow central from this commitment power, they can also coordinate the receiver's action and get the receiver to take whatever action the sender thinks is best, given the restriction of receiver rationality. You can deal with this problem also if you want to kind of account or relax the sender's ability to coordinate actions, but I'm not going to talk about that here. Okay, so our goal is to be able to kind of attack this program, and we want to attack it using the belief-based approach. The key object that's going to play a role in the belief-based analysis of that problem is what is known as the sender's value correspondence. So before introducing this correspondence, let me first extend kind of my player's preferences from being over actions and states to being over actions and beliefs using just the standard expectations. And once I have this new definition, I can write the sender's value correspondence, or I can define the sender's value correspondence in the following way. Really, what this correspondence does, it takes every belief that the receiver and the sender can jointly hold and tells us what is the set of payoffs that the sender can get when the sender holds that belief, the receiver holds the belief, and the receiver is best responding, potentially with a mixed action. So this is going to be our the central object that's going to play a role in the belief-based analysis. But to kind of explain this object and see how this belief-based analysis works, I want to make things a little bit more concrete and kind of focus more on a specific example. Okay. So this is going to be an example in which our sender is going to be a think tank who's going to give advice to a lawmaker about a reform. Our lawmaker is going to be a receiver. Now, our lawmaker is going to want to choose between one of n possible reforms and potentially kind of a status quo, but the lawmaker doesn't exactly know which reforms are good and which reforms are bad. To get information about these reforms, the lawmaker is going to consult with the think tank who's going to release a report about each reform's value. Now, the think tank is going to have some known preferences over these reforms. And in order to fit this story within the Bayesian persuasion model, we need to kind of make two assumptions about the think tank's ability to generate reports. First, the report's contents is flexible, meaning that the report can represent any kind of black hole experiment. You can justify this by thinking of the think tank as being able to kind of vary both the methods that are used for the report and kind of how the results are presented. And second, you need to assume that the think tank has commitment power. So the think tank can announce, this is the report I'm going to run. this is how the information is going to be conveyed. And the think tank cannot deviate from this plan. Now, to justify this assumption, it's still sometimes a little bit hard, but you can imagine the think tank having some transparency requirements. They have to reveal everything that they do, and potentially maybe they're disciplined by reputation and things of that flavor. Formally, the way you would kind of fit this story within this sort of Bayesian persuasion framework, you'd have the receiver's actions be any integer between 0 to n, where 0 represents taking the status quo, and other integers represent different reforms. The state is going to be a vector with n coordinates, where every coordinate corresponds to the value of a different reform. Let's say that these coordinates all lie in the interval 0, 1. The receiver's payoffs are going to be 0 if they take the status quo. And if they choose a reform I, they're going to get the value of that reform minus the cost required for executing a reform. And the sender's payoffs, let's say, are just increasing with the reform. So we ordered the reforms so that higher index reform have higher value to the sender. And the substantive assumption here is that the sender performs some reform over no reform or over the status quo. I'll also assume that the prior is exchangeable, which means that if you take a vector and you ask what's the probability of that kind of vector, and you permute it, the permutation has the same probability. That will only show up or play a role when I'll talk about this example in the context of the cheap talk model. So that's kind of a big example. I want to look at a simple example. So the simple version of this example is one in which there are only two reforms. Exactly one of them is good with probability 1/2. So either the first reform is the good one and the second one is bad, or vice versa. And let's say each reform costs 2/3 to implement. Now, what is nice about these two kind of state examples is that you can describe beliefs using only kind of the probability that they assign to one of the states. And that allows you to draw the sender's value correspondence in the belief kind of S-value plane. And that's kind of what I've done here for this simple example. So on the x-axis, I've put the probability that there's assigned to the second reform being the good one. Whenever this probability is kind of extreme, the receiver has only one best response that they can do. So if the receiver thinks the first reform is likely to be good, the receiver will only take action 1, and then the sender's value is just 1. If the receiver thinks that reform 2 is likely to be good, the receiver will only take action 2, and then the sender's value has to be 2. At intermediate beliefs, the receiver is unsure about which reform is good and then takes the status quo. And at kind of threshold beliefs, the receiver is indifferent, let's say either between reform 1 and the status quo or reform 2 and the status quo. And so then the receiver is willing to mix with any probability between those two reforms. And so the sender can get an interval of payoffs. I've also put here a vertical line that represents where our prior is, and that's going to kind of end up being important when we're talking about the outcomes that can be generated. So when we want to think about the belief-based approach, the key idea is to think of an equilibrium as being a distribution over points on this plane. And the reason we get a distribution over points of this plane is because, in equilibrium, every message that the sender sends induces two things. It induces an R posterior belief, so it induces an X coordinate, and an R mixed action, which gives us an S interim expected payoff. That's our Y coordinate. And so every equilibrium gives us a distribution over points in this space, which I'll represent in this particular way. Each one of the color dots represents something you'd get from a different message. And the black dot represents the average, which is going to be important for us if we want to understand what is, let's say, the average as payoff, right? Because our goal is to maximize that payoff. And so we'll want to kind of make that point as high as we can. So the belief-based approach asks, what is the set of belief S payoff pairs we can get in a PBE. Okay. And the conditions for this distribution turn out to mimic the conditions that we have from PBE. So the first is that Bayes' rule has to be satisfied. If you follow the algebra of the Bayes' rule in terms of beliefs, that ends up telling you that the belief coordinate must average to the prior. Okay? So within our drawing here, that means that this black dot has to live on my dotted line. The second condition that has to hold is that the receiver is behaving optimally, which in terms of this plane means that the distribution of beliefs S payoff pairs has to live on the sender's value correspondence, because that is the set of payoffs the sender can get from inducing any particular posterior beliefs, given that the receiver is rational. Okay, so that means that the distribution has to only have points that lie on our value correspondence. Okay. So we can write these conditions in sort of formal language. So a distribution, capital P, over beliefs and S interim payoff pairs can arise in a PBE only if the average posterior equals the prior. This is often known as Bayes plausibility, or the martingale condition, or the splitting condition. And the all beliefs in S payoffs must live on the value correspondence. Now, I've told you kind of why these things have to be true. It's not too hard to show that whenever you have a P that satisfies them, you can also invert back a perfect Bayesian equilibrium. And so we get an if, there's an if and only if characterization of which joint distributions of belief S payoff pairs can arise in some PBE. What this characterization allows you to do is to rephrase our Bayesian persuasion problem in the language of distributions over this space. Okay? So now we're thinking of the sender as choosing a joint distribution over posterior beliefs and interim S payoffs in order to maximize the sender's ex ante payoff, which is the average interim payoff, subject to our two conditions of Bayesian updating and receiver incentive compatibility. But we can simplify this problem a little bit more. Okay? And the reason is that since we're maximizing the sender's payoffs, given a particular belief, it seems kind of obvious that the thing you'd want to do is to make the sender's payoff as high as they can, subject to the receiver's incentive compatibility. So this means that if you're inducing a belief mu, the payoff that the sender will have to get in the solution will have to be equal to the maximum value the sender can get from the value correspondence evaluated at mu, a value that we'll sort of denote by little v of mu, and we'll call this the sender's value function. So, whenever, again, I have a distribution like this, we're going to have, a distribution of this flavor that's supported on the top of the value correspondence. Now, in terms of the program that we had from before, this is telling us that when we're looking at this expectation of S, really we should be looking at the expectation of this little v, of the value function, evaluated at the appropriate belief. But now, we can see that we're from the perspective of this program, this S is just a free variable, so we can always just make it live on the graph of V, so we can get rid of that constraint. And second, this constraint here that we have about the Bayesian updating, that only concerns the marginal of our capital P over the receiver's beliefs. And so instead of choosing a joint distribution over beliefs and sender interim payoffs, we can really just think of the problem as choosing a distribution over receiver beliefs where the average belief is the prior, and we're choosing this distribution to maximize the expected value of the sender's value function. And this is what sort of is usually known as the sort of belief-based program of Bayesian persuasion. Now, a few helpful notes about this program. First, it's a linear program in this distribution over P's. distribution of beliefs. So it admits an extreme point solution. That is nice in our finite world because you can show that the set of extreme point distributions are ones that have affinely independent support, which ends up telling us that the support of our random posterior has to be less than the cardinality of the state space. It also, this program is generally amenable to duality-based techniques. This is just standard kind of Kuntaka or Lagrangian-like results for the case where the state space is finite. For infinite state spaces, there are also some generalizations of a very nice one by Piotr Dvorchak and Anton Kotelnin that one can use. One could also use this sort of program to show that it's computationally tractable. This is a nice paper from 2016. I'll come back to that potentially later at the talk. And potentially the most famous implication of this program is that it can be solved geometrically using the notion of Kukevification. So let me talk about that for a little bit. So given my value function v, I can define what I call v hat as the concave envelope of v, which is the pointwise lowest concave function that lies above v. Within our example, this function is given by taking adding this line here and then tracing the center's first best. And so the famous theorem of concavification tells us that the value of our Bayesian persuasion program is just equal to the value of this concave envelope at the prior. And this concavification result is extremely powerful when it comes to solving these sort of two-state examples. If you think about going back to solving problem sets and stuff about like competitive equilibrium and things like that, solving these things is generally like hard. And the same thing with binary state economic models. There's, even though you can do it, it takes some time. The concavification approach is very easy. You just draw the value function, take a concave envelope, which you can eyeball, and you know what the solution is. Okay? And that is kind of probably the most powerful implication of the belief-based approach when looking at the Bayesian persuasion. So that's what I want to say about Bayesian persuasion. Let me spend the rest of the tutorial talking about the other extreme case, which is the case where there's absolutely no commitment for the sender. Right. So with Bayesian persuasion, the sender can communicate to any information structure that they want, to any black hole experiment. Now we're going to consider the case in which the sender cannot commit at all. So this would correspond to the model of cheap talk. So specifically, we're going to think about kind of the following timing. Now, instead of the sender committing to an experiment at the beginning of time, the sender is going to see the state and then send the receiver a single message, okay, given that state. The receiver is then going to see the message and take an action just like in the Bayesian persuasion model from before. Okay? And so it's this fact here that the sender sees the state before sending the message that generates a commitment problem for the sender, because the sender now might want to send different messages depending on what they want the receiver to do. So, now we're going to have to amend our solution concept. It's still going to be, I'll still call it a PBE, and it's still going to consist of 3 maps. But now, instead of having a sender experiment, we're going to have a sender strategy. It's still the same formal object, but we're going to interpret it differently. Instead of thinking of the sender as committing it at the beginning, we're going to think of the strategy as representing, what distribution over messages the sender sends after seeing the state. And, in addition to the 2 conditions that we had from before of Bayes' rule and the receiver optimization or receiver IC, we're also going to have a sender IC constraint or a sender optimization constraint, which tells us, that for every state that can arise, the sender only sends messages that maximize the sender's expected value given the state and the receiver's strategy. Now, the main kind of annoying thing about this constraint is that you have it theta by theta. So you're going to have a different IC constraint for every state. And that generally makes it hard to apply the belief-based approach to this cheap duck model. You can kind of do it by looking at things like Alma and Hart. And I think Elliot will touch upon that maybe very briefly in his part of the tutorial. But it's difficult to do because you generally need to trace payoffs of the sender across all types. So as I kind of anticipated in the beginning of this part of the tutorial, one exceptional special case that is very amenable to belief-based analysis is the case of what we call transparent motives. So this is the case where the sender's payoffs do not depend at all on the state. So you could just think of them as being a function of the action. And this assumption, it's kind of extreme, but there are a lot of applications where you could think of it as being a realistic description what is happening there, or at least a good description. Politicians who want to get elected or want their policies implemented. Salespeople want to sell you their expensive products. Job applicants would like to get high-paying jobs and things of that flavor. And the reason this kind of assumption is useful is because it simplifies our incentive constraint. Okay, so if you look at the incentive constraint from before, the first thing that you're going to realize that drops out is the dependency of the state in the sender's in this sender's expected value. And in fact, you can actually rewrite this constraint in an even more tractable, revealing form. And this rewrite tells you that for any message that the sender sends, it must be that the expected value that the sender gets equals to the highest expected value the sender can get across all messages. So it's telling you that this interim expected payoff the sender is going to get is going to be constant. It's going to be equal to this maximal value. So how are we going to incorporate this constraint into our sort of belief-based analysis? Well, what we're going to do it is we're going to augment our distribution over receiver posterior beliefs that we had before with an additional number, which is going to be denoted by S, and that's going to be the sender's ex ante payoff. And now, once we do this little augmentation, we'll be asking which PS pairs can arise in a perfect Bayesian equilibrium. So to ask that, let's go back to kind of our sort of little value correspondence from before. And remember our conditions that we had before about the joint distribution of beliefs in S interim S payoffs that we must have. In the Bayesian persuasion model, we have only two conditions, the Bayes rule condition and our optimality. Now we have the additional constraint of sender optimality, which tell us that the sender's payoff coordinate has to be constant, right? Because if it's not constant, the sender never is going to send the low payoff messages. They're all going to send the high payoff ones. So this means that the kind of distributions we're going to have to have this kind of form here, where the sender's interim S payoff is just constant. But if the interim payoff is constant, then that interim payoff is just equal to the sender's ex ante payoff, that little s that I introduced before. And so we get that P and S can arise in a perfect Bayesian equilibrium of our cheap duck with transparent motives game if and only if two conditions are satisfied. The first is our Bayes plausibility condition from before. So this means that the average posterior equals the prior. And the second condition is that whatever posterior is being generated by your, this little p, that posterior must enable the sender to get their ex ante payoff as an interim payoff when the receiver best responds. And so we get this sort of belief-based characterization of what can arise, which PS pairs can arise in a PBE of the transparent motive cheap talk game. Now, this characterization, it's written pretty succinctly, but it still has this somewhat scary intersection condition. And so one of the kind of two main results, or perhaps the main result of my paper with Elliot, gives us a way of trying to kind of get away from this intersection and study something a little bit easier. And that is going to be the notion of securability. So to describe securability, let me first introduce notation for the set of distributional or posterior beliefs that average up to the prior. Okay? I want to use the script P of mu naught to describe that. So I'm going to say that one of these distributions secures some value S if it, with probability 1, generates a posterior belief that allows the sender to get the value of S or higher when the receiver best responds. Okay. And I'm going to say that the value S is securable if you can find some P that secures it. So in the example from before, if I look at the distribution like this kind of a sort of slightly magenta or brownish one here, that distribution would secure a value that's equal to this dotted line because, posterior by posterior, the sender gets a higher value than this dotted line. And so perhaps what is our main theorem in our paper says the following. Suppose you give me an S that's higher than the value the sender can get under the prior. Then that value is SPBE as a payoff, as a sender payoff in a sum PBE, if and only if that value is securable. Okay. Now, one side of the implication is easy. If something is a sender payoff in a PBE, you have that information, that random posterior, that little p that always gives you that value no matter what message is sent. The converse proof is constructive. I don't have time to kind of go over it in the tutorial. But roughly speaking, what you do is you kind of walk on the sender's value correspondence towards the prior until you hit the value that you need. Because there's some intermediate value theorem logic that tells you that you're going to be able to do it. And then that's what gives you sort of the value or the little p that gives you this S, message by message. So that's, in some sense, the main kind of theorem that we have. And then once one has this theorem, one can try to kind of compare what you can do with cheap talk to what you can do under Bayesian persuasion. And, to describe this, remember that we said that under Bayesian persuasion, the highest payoff you can get with this commitment is kind of the concave envelope of the value function evaluated at the prior. Turns out that using securability, you can get sort of an analogous result for cheap talk. In particular, you could show that the highest value the sender can get under cheap talk in the state-independent preferences case is given by the quasi-concave envelope of the sender's value function evaluated at the prior. So the quasi-concave envelope of the value function is defined analogously to the concave envelope. So it's given by the point-wise lowest quasi-concave function that lies everywhere about the value function. Now, because every concave function is quasi-concave, but not every quasi-concave function is concave, this is immediately telling you that the sender's value under cheap talk is weakly below the Bayesian persuasion value. That's a good sanity check. But one can actually use, one can use this thing more to get a better, tighter result. But this geometry also actually kind of informs you a little bit about the difference between Bayesian persuasion and cheap talk in this transparent motives case. So, what the concatenation does for you is allow the sender to increase their payoff by kind of connecting points on kind of the value correspondence using any kind of affine segment that you want. And when you do that, you get some sort of nice kind of function that looks like you took your original function, put a rubber band around it. What happens with CheapDoc is that with transparent motives is that you can still benefit from kind of connecting points in the eval correspondence, but now you can only use kind of flat segments. Okay? And that's what happens here. In the two-dimensional case, you can think of this as like rain filling up the valleys. Doesn't quite work with more. And this geometrical difference kind of allows you to show that within our finite setting, almost no matter what belief you give me, either there is no point at all in communication from the setter's perspective because they can get their first best value at the prior from CheapDoc, or commitment is going to be valuable. Okay? And I don't have exact time to explain how it works, but roughly speaking, use the quasi-concave structure of the quasi-concave envelope to find a splitting that strictly benefits the sender that cannot be communicated with CheapDoc. So I believe I have about 5 more minutes, maybe a little bit less. I'll use these 5 minutes to kind of just demonstrate how you apply the securability theorem to that big think tank example that I gave you what seems like a long time ago. So remember, this is kind of our think tank example from before. The sender gives advice to a lawmaker about a reform. Now, to interpret this thing within the CheapDoc model, we're going to think of the think tank as knowing the value of each reform. But also, the think tank's preferences are known to the receiver, to the lawmaker. Let's say the lawmaker might know the think tank's political leanings, and so that means that they know they might prefer maybe more market-based reforms or more government intervention-based reforms, depending on the think tank's politics. And so, this is kind of what the formal structure of the example, right? And now, the exchangeability assumption from before is going to play a role, and I'll add this requirement that there are no ties just to simplify some of the discussion. So how do we apply securability to this example? Well, securability is going to actually allow us to characterize what is the set of values that the sender can get in some equilibrium. In particular, using securability, one can prove the following kind of result that says that the following 3 things are equivalent in this example. First, integer k can be attained as an equilibrium value for the sender, okay, where k is between 1 and n. Second, the expectation of the maximum value of the state or the value of the reforms to the receiver among the reforms that are indexed k or higher is larger than c. And 3, so the first 2 things are also equivalent to 3, to s, the sender being able to secure the value k by revealing which among the k, the reforms indexed k or higher are the best for the receiver. Now, don't have a lot of time to talk exactly about the proof. The fact that 1 implies 2 ends up following from the lawmaker's ex ante incentives. If the lawmaker is willing to give the sender a value of k in equilibrium, that means that they're always willing to implement some reform indexed k or higher. That means that if the receiver knew what is the best reform among k or higher, they'll be happier to do that than to take a status quo, which it gives you 2. The fact that 2 implies 3, for that you need to use exchangeability assumption. Let me just leave it at that. And the fact that 3 implies 1, that's exactly our securability theorem exactly tells us that, because if you can secure a value of k by revealing this particular random variable, securability tells us that you can get k as an equilibrium value. Now, the reason this claim is helpful is especially because of point 2 here, because point 2 gives us the tight condition as to which kind of equilibrium values the sender can attain. And so if you want to find the highest value a sender can get, all you need to do is to find the highest K such that this condition is still satisfied. And that's what this K star will be. And that's what gives you the sender's preferred equilibrium value here. I don't want to talk too much about this, but you can also use the securability construction, the way we get an equilibrium from a securing distribution over posteriors, to find exactly what is the sender preferred or a sender preferred equilibrium. This one involves kind of with the sender randomizing between telling the receiver what is the best reform among the K star or higher, and just uniformly kind of recommending a reform without it being, irrespective of what the state values is. And that allows you to calculate explicit expressions for the sender's optimal value for specific cases. Let's say for the case where the states are IID uniform, and also analyze kind of the value, do something about get bounds on the value of commitment in this example. So the difference between what you can get under cheap talk and what you can get under Bayesian persuasion. Now I should say that the general example, solving it with Bayesian persuasion, is hard. At some point we managed, at least for us, it was hard. I don't know, maybe it's easier for others. At some point we managed to solve kind of like a 3 reform example, but beyond that, it sort of extended, exceeded our capacities. So yeah, I kind of am running out of time, so I'll just mention that it turns out you can use securability to also show that the state-independent case of cheap talk is finding the optimal value is computationally tractable. This is shown in a paper that I think is going to be presented in this edition of EC. And so I'm very excited to see it presented. Yeah, so I think, we've reviewed Bayesian persuasion and the belief-based approach there, and looked at kind of the special case of cheap talk that's amenable to the belief-based approach. And in the next part of our tutorial, Elliot will talk about kind of intermediate cases. And that's it for this part.